In this video, we talk about the reaction quotient in the context of chemical equilibrium. Let's first draw a chemical equilibrium that is generic. Let's think about the reaction of A to give B, which is reversible and it reaches an equilibrium. And we can tell that reaction reaches an equilibrium because when we plot the concentrations of reagents A and products B as a function of time, we get plots that look like this. That's a plot of the concentration as a function of time. If we start the reaction with only A reagents and no B products, the plots that we should get might be something like this. Okay, that will be 1, this is A, and then this would be B. Okay. Now notice that there's a point in which the concentrations no longer change on time, and that is the point in which we reach equilibrium from here on. Now we can quantify the equilibrium, the equilibrium by writing here the equilibrium constant, which by the law of mass action is simply the activity of B over the activity of A. Okay, the stoichiometric coefficients are 1, so here we have those powers as 1 and 1. And if we assume that these are solutes in an aqueous solution, then we can simplify this in shorthand notation as the concentration of B and the concentration of A. Now, this equilibrium constant is important to define it after equilibrium has been reached. Okay, so these concentrations that we have right here are those that happen right after equilibrium has been reached. We can further specify this by writing here subscripts EQ, again to reinforce the idea that those concentrations must be after equilibrium has been reached. Now what we could actually do is write the same ratio of concentrations of products over reagents at any point during the reaction, not necessarily at equilibrium. Right? So we could take, say this time, and then get that concentration of A and that concentration of B, and then write the ratio of those two. That would no longer be the equilibrium constant, it would be something different that we call the reaction quotient. Okay, so the reaction quotient is this Q, and again this Q would be exactly the activity of B over the activity of A, which for solutes in an aqueous solution would simply be the concentration of B over the concentration of A in shorthand notation. But an important distinction between the reaction quotient and the equilibrium constant is that the reaction quotient can be written at any time. You don't need to be at equilibrium to write this. Okay. However, to get the right value for the equilibrium constant, then those concentrations must be those at equilibrium. Okay. So you can clearly see that the reaction quotient is a much more generic version of the law of mass action than the equilibrium constant. Or in other words, you can clearly see that the equilibrium constant is kind of a specific case for the reaction quotient, which takes place once the system has reached equilibrium. Okay, now there's something interesting about the reaction quotient and the equilibrium constant, and that is that a comparison of the two tells you whether the system wants to move from reagents to products or whether the system wants to move from products to reagent. Okay, so I'm going to write here a particular value for the equilibrium constant. If we take a look at this particular reaction that we have right here, notice that we have a little bit more of A than we have of B at equilibrium, right? So we can say that the equilibrium constant is going to be perhaps about 0.8 or so. And I'm making these numbers completely up. Okay. Now let's try to figure out what would be the reaction quotient at this particular point. Okay, will we actually have even more A than B? Okay, notice that at this particular point we can say that the ratio of A and B is perhaps going to be about 0.5 or 0.6. Okay, what we can clearly see is that the reaction quotient at this point is smaller than the equilibrium constant. Okay, so when that is the case, what we can actually do is say, well, what is the direction for change as the system looks for equilibrium? Okay, well, if the reaction quotient is less than the equilibrium constant, that means that as the system goes by, the reaction quotient is going to increase its value until it reaches the exact value of the equilibrium constant. In this case, in order for that to happen, the value of the reaction quotient has to grow, and that can be by either increasing B or decreasing A, or both. Okay, so what has to happen is that in going from where you are right now at this value of the reaction quotient to equilibrium, then you have to generate more B, and then you have to reduce the amount of A. What that means is that when the equilibrium constant is less than when the reaction quotient is less than the equilibrium constant, then the system has to displace from left to right. Okay, so notice that again the reaction quotient is a very useful signpost for where the change is going to occur. Okay, if we have a reaction quotient that is less than the equilibrium constant, then that means that the equilibrium has to move from reagent to products, because that value has to increase, and the only way to increase is if you increase the amount of product and diminish the amount of reagent. Conversely, in a different set of initial conditions, not these ones, but some other ones, we can actually come up with a value in which the reaction quotient might be larger than the equilibrium constant. Let's assume that for the sake of discussion, now we're going to discuss a case in which, well, we have that this ratio of concentrations has to be 1.0. Okay? Right. Notice that the value of the reaction quotient, in this case 1.0, is larger than the equilibrium constant. So by comparing these two Q and K values, then we can predict what will be the direction for change. Okay? So what we have is that under this particular set of conditions, we have that the reaction quotient is larger than the equilibrium constant. In order for this to make it smaller and reach equilibrium, reach K, what has to happen is that this has to increase, and that is reagents, and this has to decrease, this is products. Okay, when we go to the chemical reaction here, this has to increase, and then that has to decrease in order for the reaction quotient to drop from 1.0 to 0.8. What that means is that for this particular case, the reaction is going to move towards the left. Products are going to back react to generate reagents. Okay? So you can clearly see in this video how after defining what the reaction quotient is, we can use it as a signpost for the direction of change. If you calculate a reaction quotient under some set of conditions that is smaller than the equilibrium constant, then if you let the system evolve, the system will move to put more reagents in the products before equilibrium is reached. Conversely, if under a different set of conditions you find that the reaction quotient happens to be larger than the equilibrium constant, then the equilibrium is going to move by reacting products back to reagents before equilibrium is reached. Okay? So that again corroborates the idea that from the comparison between the value of the reaction quotient and the equilibrium constant, we can predict the direction of change of that particular chemical reaction.